Okay, quickly, welcome to the Young Modular Solutions. This is a very simple task. We want to go into implicit differentiation, and these are the following rules you have here. But I may not actually follow this rule accordingly. Okay, I will give you the simplest method you can use, which is accepted in any exams. Okay, normally, whenever you have a function, okay, you have a function. Let's say y equals to 2x plus 5. This function is said to be an explicit function in the sense that we are not differentiating with respect to y, we are only differentiating with respect to x. So whenever I differentiate with respect to y, it becomes an implicit function. Okay, so if you look at the rule, you can follow the rule accordingly. I know many of you are very conversant with this rule, but I want to show you a very simple trick you can use to do your implicit differentiation. Okay, we'll not follow all this process. If you look at here, step 1, step 2, step 3, step 4, we don't need to follow those steps, especially when it involves exam like this. Whether the exam is theory or objective, you can apply this rule that I want to give to you. So we'll be applying this rule to solve this very problem. Look at the problem we have before us. So I'm not going to show you this one as I did earlier. So I will only go through it accordingly, but you can just feed your eyes on them. You can just feed your eyes on them, on their steps, the long steps they are using. You can go through it, the long steps they are using. Okay, you can go through the long steps that they are using to solve the problem. I may not actually go through those long steps, but I will give you the results and you can confirm our answers accordingly. You can see it there. All right. Okay, this is the formula we want to be using. It's as simple as this, a very straightforward formula in a solving implicit function. Now this formula, the condition you must fulfill in using this formula or this rule is that every function on the right hand side must be brought to the left hand side. So for example, if I have here, like for example, I have here 6x. So you must bring this x to the left hand side before you can apply this rule. But for this number, and this number is not necessary, because even though you differentiate a constant, you get 0. But whenever you have a function like this, that is not a constant function, whether linear, quadratic, or something, you bring it to the left hand side. That is only when you can apply that rule. Okay, quickly let's look at that. So now, in doing that, let's interpret what this rule states. It states that you are going to differentiate all the terms containing x and drop it on the numerator, then differentiate all the terms containing y and drop it at the denominator. That's what this rule is talking about. So that's what we are going to be doing right now. Okay, so now looking at the first question we have here, we have here x cubed plus x cubed y cubed plus y cubed. So the first x term I have is x cubed. So I'm going to differentiate x cubed. So if I differentiate x cubed, I'm going to get 2. I'll get 2x squared. Alright. Then the next thing again I have now is x cubed y cubed. Remember, x cubed y cubed is a term. So we will keep the y cube constant, we will not touch it. Then we'll only work on what? X cube. So we are going to get 3x. So the first one is 3. The first one is 3x squared y squared. 3x squared. Sorry. Because we have x cube here. So if we differentiate using power, we are going to get 3x squared. So why this one now 3x squared y cube. Then that y cube is standing alone. So we treat it as a constant, we eliminate it, which is what? 0. Then divided by, we now differentiate what? Using the rule here, we differentiate the y term. So the x cube will now be a 0 because we are dealing with y term. Now coming to x cube y cube, we differentiate with respect to what? Y. So we now have 3 in front, x cube being constant, then y square. Alright, then plus 3y square. So you can see that. Alright, you can see that. Okay, so if you want to factorize that, yes, you can factorize that 3 up here. You can factorize out 3s squared here, then into, there's a minus sign here in front, then into 1 here plus y cube here. Then the same thing here also, we can factorize out 3y squared into s cube plus 1 here. Okay, so if we check the main answer, you also see the same thing there. So after factorizing, you have this. Okay, you have this. Remember, 3x squared is common on the numerator, y3 y squared is common on the denominator. Then you rearrange it. Okay, just the rearrangement we have. It's still the same thing anyway, but you rearrange it. This is what you get. Now let's go through their long method and see the answer they have. Yes, so we have the same thing here. So you can see it down here. We have the same thing here. So you can compare this to my results. So it's the same answer you get. All right, from there. So looking at the second one, so you have this down here. If you differentiate in terms of x, first of all, you are going to bring this 6x down here, inside here, like I said. If you differentiate this, you are going to get 2x y squared. Then when you bring this down, you are going to get minus 6 when you differentiate 6x, minus 6x. Okay, and that is exactly what we have here. Then if I do it in terms of y, differentiate in terms of y, you are going to get 2x squared y, then minus 1 down on the denominator using the rule. This is what you get. Okay, so the with respect to x function on top, the derivative on top, then with respect to y function, derivative down. So you can see their own results. They just reverse the position of the 6 up there. When you open the bracket, remember we normally have a bracket, a minus sign before that numerator. So if you open the bracket, this is what you get, which is the same thing. Alright, so let's go to number 2. So in number 3, C. So we have, it's like a product rule we are going to be applying because we have x and y equals to 1. Okay, so in doing that, I've just written the product rule up here, u v prime plus v u prime, any of them. So our u here is x, our v here is sine y. So u is x, so v prime means differentiate with respect to y. Remember, we are doing up there, we are doing with respect to x. So if you differentiate with respect to y, you are going to get 0. Okay, then plus v u prime. Now our v there in this case now becomes sine y, while our u prime there is our u. So if you differentiate our u prime, which is x, we are going to get 1. So down there also, you also look at the denominator, is the same thing. You apply product rule also, but with respect to y. So in that case, we have our u, which is x, then v prime is our v prime, which is differentiating sine y, we are going to get cos y. Then plus our v, which is sine y, then the u, okay, which is our x. Since we are dealing with respect to y, our sine x, our x becomes 0 when we differentiate it. So when you do the evaluation, or you get this. Okay, so learn how to apply your product rule. One thing about implicit differentiation is that every aspect of differentiation can come in both trigonometry, exponential, and logarithm can come in. So you need to know those ones properly to enable you to do the implicit of this function. Okay, so by the time you cancel out this time this is 0, you have this time this is 0, you have this sin y over this. So if you divide sin y against sin cos y, you are going to get tan y. So while the x remain down there, so this is the final result. So you can look at their long method, they also arrive at the same thing. You can see there. Then if you come down here too, they end up getting this. You can see there. All right, so the last one, the last question, that is question D, we have here, we are going to apply our chain rule, cos xy plus 4x. Now when you differentiate cos xy with respect to x, if you differentiate xy with respect to x, we are going to get y. And if you differentiate xy with respect to y, you are going to get x. So and you know that in our chain rule, whenever you differentiate what is inside, you use it to multiply the function, the derivative of the function. All right, so we end up having something like this. So if you differentiate with respect to x, the y will come out. We use it and multiply the derivative of the function, which is this. Then we repeat our xy. Then if you differentiate our 4x, we'll get 4. The 8 is constant, which is 0. Then the same thing here also down here. If you differentiate with respect to y, this original function, do with respect to y. Remember, the down part is the y part, the up part is the x part. So you have x minus x sine y. So when you open bracket, you end up getting this. All right, end up getting this as a final result. So if you also look at their long process too, you also get the same thing. Okay, just that they just position their stuff. So you have the same thing. They brought the minus 4 before the y sine xy. So it's still the same thing. And then in this case, Yes, okay. I think I omitted my minus, so the minus still remain here. Nothing cancel out. Okay, nothing cancel out except we wish to cancel out from the beginning. Okay, if we cancel out from the beginning, fine. Then the minus will go off. But if not, the minus still remain as they have there. All right. So that's that for that. So we'll be going into integration soon. Okay, we're going to integration right now. So